energy, and where the total energy of this electron which remains constant and the stationary orbits. From the higher energy level to the lower energy level, emitting which to takes place, or else you have to say that when the electron which is to be jumping from the lower to the higher energy level, then the absorption should takes place. Both these cases, how the radiation of the frequency of the radiation which is to be calculating here, that is E2 minus E1 by H mu equals to, that is already discussed here. The case for the atom which is consisting of a nucleus, the charge of the nucleus is Za plus Ze. Okay, and where capital M the is the mass and so for this condition, there is a mechanical stability of electron Coulomb attractive force which should takes place. Then the electron must be equal to the centrifugal force which is given by mv square by r. So you have to equal to mv square by permittivity of the free space. In some cases, you have to write everything here. That value Newton meter square per Coulomb square. So that here, what is the force which is to be acting upon the particle to accelerate around in such a around the nucleus in such a orbit here? Then you have to say that what is the angular momentum here, orbital angular momentum, which is always constant here. That is L equals to mvr. You know that L equals to mvr, which is equals to here h cross, that is nh by 2 pi here. That value should be equals to h cross, where h cross equals to h by 2 pi, most important bit, h cross value. And by substituting in above equation, v equals to nh cross by mr. And by doing this calculation, we are to be getting that what is the radius of our orbit, which is always proportional to the square of the quantum principal number n square. So that which is called a quantum number, and n equals to 1, which is related to the hydrogen atom. By substituting these equations, you are to be getting that what is the radius of the first orbit, which is 5.28 into 10 power minus 11 meters. Similarly, by doing this, you can easily calculate the what is the potential energy of an electron, which is to be revolve around the different orbits around the nucleus. So that is to be calculated. And later on, you have to calculate that what is the total energy of this. So that how do you calculate the total energy here? By adding the sum of the potential energy as well as the kinetic energy. So you have been calculated the potential energy value, V value. Later on, you have to calculate the what is the total energy. That is kinetic energy T equals to half mv square. By substituting the V square value, this you are to be getting here T value. So the total energy which can gives the sum of the potential energy plus kinetic energy, E equals to T plus V. Okay, T is a kinetic energy. So substituting these values, you could be getting here, and E equals to this much value, where R is the value which is nothing but a Rydberg constant here. So that what is the energy level of the hydrogen atom, for which consists of only one electron. So that the energy which is to be noting that here n value, which is to be increases from the ground state to this one, the energy which is also to be varied here, that value should be, you can easily observe that. Okay, so this must be very very important equation. Later on, frequency value to be calculated here, mu equals to E2 minus E1 by H. Okay, whatever it may be, some textbooks they are going to be writing here EI and as well as the EF. EI means here initial, F means the final value, so that you need not to be worried about this equation here, mu equals to, why? Because of the radiation which was proposed by the Max Planck, E equals to H nu, so that nu is the frequency, nu equals to E by H. That means here the delta E, which is related to the how the change in the energy which is to be takes place, that should be observed. So that's what here you to be calculating here frequency value. So that should be equals to 1 by some value into 1 by nf square minus 1 by ni square. You know pretty well the equation which is c equals to nu lambda. Why? Because of here nu by c equals to 1 by lambda. Again you have to be substituting the values. So that is K equals to 1 by r infinity into 1 by 2 square 1 by nf square minus here. So that so in which condition the Balmer as well as the Lyman partial bracket fund series is to be observed here. So that when n equals to 1 and final value 1 and n initial partial bracket, okay, and also is to be observed. So this is the energy level diagram of very very important. So so that means here which is to be giving here in which condition you will get the Lyman series as well as the Balmer Paschen bracket fund series is to be observed. That is to be noted here. So when n equals to 1 to infinity, so like so this is the most important essay question later on, Sommerfeld. Okay, so what you can the Bohr's theory which is fails here. Why? Because of here which does not explain the more than one atom here, only for a single atom which is to be giving out here how the spectral lines to be observed and how the energy levels to be calculated here. Okay, how the line spectra of the hydrogen atom which is to be giving out, that is for only one single atom, more than one atom is to be there. So is that Bohr's explanation is which is sufficient to explaining all these categories? Not at all. Why? Because of which is failed here. So later on, Sommerfeld is entered into this concept here to explain, so that uh, the hydrogen spectral lines have well-defined wavelength, but according to the experiments here with the high resolution spectrograph, which is to be shown by this, so that a hydrogen spectra which includes the line spectra, so that you can easily observe that what is H alpha, H beta, H gamma, H delta, like that. Okay, so which are very very close lines packed together here. And also later on Michelson, he have been found that H alpha line consists of two close components which are to be separated by a wavelength difference is 0.013 angstroms. 1 angstrom is like nothing but here minus 10 power minus 8 centimeters or 10 power minus 10 meters here. So these are known as a fine structure of spectral lines. So where do you observe according to this? If you see the what do you say here? Sodium vapor lamp, yellow color light. There only you can easily observe that two lines. One is that here 5890 angstroms. Another line is that 5896 angstroms. Combinationally, you are going to be saying that 5893 angstroms for yellow color. Only for yellow color spectral line, you are to be saying that 5893 Armstrong's here. So that there should be a resolving power of a grating. Okay, the resolving power of a telescope, not a grating, resolving power of a telescope by using the yellow color single monochromatic light. You have to be performed an experiment. Experimentally, you can easily observe that condition. So similarly for hydrogen atom also they have been calculated and shown that here the hydrogen spectra for H alpha line, what is the wavelength difference? We have been observed that here 0.0 here 13 angstroms. Fine structure of the spectral lines, and also which could not be explained why it is to be happening by the Bohr's theory, so that which can give the here Sommerfeld, which can done two modifications for the Bohr's theory. What is that modification? Electron which is to be revolve around the nucleus here in an elliptical orbit. What do you say? What do you say? Elliptical orbit, not in a circular. So that Bohr is to be considered that the electron which is to be revolve around the nucleus is in circular orbit, which is to be revolve around the nucleus is in a elliptical orbit. What is the secondary case? Second case is that here the velocity of an electron moving in an elliptical orbit varies. That means varies means it is to be changing. Okay, so sometimes it is to be increased, sometimes it is to be decreases here. Varies considerably at a different part of the orbit here. So why it is to be causing here? Why it is to be happening here? This causes the relativistic variation of the mass of the moving electron. So that which is to be known as the relativistic model of the atom here. So these are the considerations here why the Sommerfeld is to be entered. Okay, so you have to discuss about that. What are these equations here? Let you have to consider that electron which is to be moving in elliptical orbit around the nucleus, so that its position at any instant which is to be given out by which is the small r, and the distance between the electron and the one of the force of the ellipse, which is always known as here radio vector, and also phi is the angle between the vector to the x-axis, or what is the major axis of an ellipse. Okay, whether it is a major axis or minor axis. Okay, so according to the Bohr's quantum condition, what is the momentum which is to be associated with these two quantities? How these are to be quantized by following this equation: integral p phi d phi equals to n phi h, and also pr integral pr dr equals to nr h. So where n phi and n are the known as azimuthal and radial quantum numbers. Okay, so azimuthal, which is always known as angular quantum number, and which should be takes always in a positive integer, and their sum should be equal to the n, so that you can easily determine how to calculate these two equations by considering 0 to 2 pi to p pi. Why to be considering here p 2 pi means around the entire elliptical orbit to 360 degrees. That's why you have to consider 0 to 2 pi p phi d phi equals to n pi h. So by doing this equation, by simplifying this equation, you have to be getting clear what is n phi value and what is a and b values. So you should follow this. And also here they have been calculated that what is the energy, total energy, which is to be considered. Okay, later on, energy level of an hydrogen atom. Uh, so the hydrogen atom energy level is Rydberg constant here. Nu bar equals to 1 by r into 1 by nf square minus 1 by ni square, that equation. So there only have been calculated where the transition is. Next one is the vector atomic model, most important expected essay question. So in this vector atomic model, you need to be know that here what is the spatial quantization. Okay, so according to the Bohr's theory, the orbits which are to be quantized, that should be whether it is in a size, from only, but quantum theory which is to be consist of quantization of orientation of the orbits in a space or simply in the direction. So for this purpose, here when the magnetic field which is to be applied, the atom is to be taken here, so that how the projection of the quantized orbits in the field direction, which is also to be quantized here, only such orientations which is to be permitted here. So this principle of space quantization could be explained by the splitting of the spectral lines, splitting, okay, of the spectral lines under the application of the magnetic field as well as the electric field. Magnetic field splitting of the spectral lines by applying the magnetic field, which is related to the J1 effect. Magnetic here the spectral line splitting of the spectral lines by applying the electric field, which is related to the Stark effect. Okay, so that is to be considered here. These two are to be performed by the space quantization. Next is the spinning of the electron, so that how the spinning of the electron which should be takes place here, whether is it in a upward direction or a downward direction. Upward you have to be considered as a positive, and downward you have to be considered as a negative here. So the spin of the electron is a plus of to minus of, that is to be considered here. And also here, if you want to explain the fine structure of the Uhlenbeck and Gaudsmit, they have been introduced the concept of spinning electron. So according to this, the electron spins about the axis of its own addition of orbital motion. So quantum theory, which insists of the quantization of the spin also, and here a new quantum number which is to be introduced, that is nothing but S here, so that S have the both orbital and spin motions quantized in magnetic magnitude as well as the direction, which is to be known as quantization vectors here. So this model you can call it as a vector atomic model. How the quantum numbers which are to be associated with this vector atomic model. So that first one is the principal quantum number, which is to be denoting here a small n, and according to this, the number of the shell of from the Bohr's atomic model, so that it can be taken as n equals to 1, 2, 3 like this. Next, orbital quantum number, which is to be denoted here as small l, and which can take any integer value which includes the 0, so that here which is similar to that of the azimuthal quantum number n pi according to the Sommerfield's theory, n equals to 3. How the L values is to be considered here 0, 1 and 2. If L equals to 0, then it represents the selection, and if L equals to 1 represent the p electron, so that if L equals to 2, it represents the d electron, and so on. So what is the total orbital angular momentum PL of an electron, which is nothing but a PL equals to here L into h by 2 pi. But according to the wave mechanics, this should be equals to square root of L into L plus 1 into h by 2 pi, or else you have to write it down h cross. Why? Because of h cross equals to h by 2 pi. You need not to be worried. Next, spin quantum numbers. This is also to be equal to that of the here square root of s into s plus 1 to h cross or h by 2 pi. Next, what is the total angular momentum that is to be considered here J value? So orbital as well as the spin motion, which is to be equal to the here total angular momentum. So J equals to L plus S. So that should be considered here, right? Square root of J into J plus 1 into H cross. So that which is to explain the splitting of the spectral lines, we have to consider more number of quantum numbers when the magnetic field is applied to that. Next, magnetic orbital quantum number, ML, not into ML, M suffix L. There is a print mistake, you can observe. The projection of the orbital quantum number, small l, on the magnetic field direction, which is known as the magnetic orbital quantum. Okay, so which can vary from the minus L to the plus L, and also includes the 0 value. Okay, so here the L vector, which can take the fine orientation around the magnetic field, and which is the direction which have been already shown this figure. You can easily observe that. So if L equals to 3, How the ML values is to be considered here? 0 to -1, -2, -3 downwards. Upper direction is 1, 2, 3 like that. If L equals to 3, ML values is here -3, -2, -1, 0, 1, 2, 3 like that. The field is magnetic field is in upper direction V1. So which is nothing but this is known as a spatial quantization. Next, MS value, magnetic spin quantum number. So here the projection of the spin vector S value along the direction of the magnetic field, you can see here. Okay. So we can assume only two values, plus of to minus of. MS value is plus of upward direction, downward direction is MS value is minus of. That's it. So these two spin vectors may be parallel or anti-parallel. Okay. Next, magnetic total angular momentum quantum, MJ value. So the projection of the total angular momentum vector J on the direction of the magnetic field, J value is L plus or minus S. Okay, L plus or minus S. So that here L plus S or L minus S, comma, and MJ, which can have the only odd half integrals. Okay, so that 2J plus 1 values, which can varies from the minus J to plus J, including the 0 values. See here, same figure. Okay, J values and also J values plus of, so minus of, as well as the, like that. ML value, MJ values, we have to receive. Next one is a Frank Hedge experiment. So this how the Bohr's theory of atom is to be will be in the ground state. The electrons revolve around the first orbit. Later on, atom is to be radiate the energy. Electron from the ground state should be raised to the higher energy state. So that this process we can call it as excitation. Okay. If the excitation is high, such the electron is knocked out of the atom. This process is known as ionization. So the potential that are necessary for the above two processes. One is that excitation, another one is the ionization. Okay. So by the excitation high, the excitation is very high, the electron is knocked out of the atom. Okay. That is the ionization. So which is known as the two processes known as critical potentials. So excitation potential, which is always known as radiation potential or resonance potential, and these potential which are to be expressed in the electron volts. So for a hydrogen atom, there is only one ionization potential because it can have several excitation potentials. So in case of atom with more number of electrons, so there can be a more than one ionization potential. That is to be observed. So what is the energy required to remove an outermost electron, which is known as the first ionization potential? For required to remove the second electron is a more attached to the nucleus because of there is a strong attractive forces to be takes place. So that's why this is nothing but a second ionization potential, which is greater than that of the first ionization. So for helium, how many atoms are there? It can consist of 2, so that atomic number is 2 here. So that how many it is needed? 2 ionization potentials. So what are those? At 24.5 and 78.6 electron eV. So what are these? Are the critical potential which can be determined by an experiment, and according to this helium atom by the Frank and Hedge. So they have been studied the critical potential for a mercury vapor lamp. So this is an aperture apparatus which consists of a glass tube. Capital T is a glass tube which is filled with a gas here. And also whose critical potential are to be determined for the at a pressure of 1 mm of mercury. So you can easily see that electrons which are to be produced by heating a filament F. F is a filament here. So by applying such a voltage here or a battery through the battery, these electrons which are to be accelerated towards the F performed plate capital A, so which is known as a grid by giving a variable positive voltage with respect to the filament, and the electrons which are to be collected a plate P, which is given a small variable negative voltage from the battery, so that the electron are having energy which is greater than that of the small voltage which can be reached by the plate P here, and how much of the current which is to be constituted by these electrons which can be measured by the ammeter. Milliammeter is there, 10 4 minus 3 ampere. Okay, so how the voltage uh, of the battery which is kept at a constant uh, at a very low value, so that when the battery B2 value which is increased slowly, the plate current which is to be noted here P. Plate current means electrons which are to be reaching out from the filament towards the plate P here. There only you are to be collecting. By using the milliammeter, you are to be calculating how much of the current which is to be passing through that. Okay. If the B2 value is varying here, that's what here you can easily observe that there is a variable is there. That means if B2 is varies here, how much of the current which is to be constituted by the plate, that is to be known. Slowly you are going to be increases, the plate current is also to be. So you can plot a graph between the accelerating voltage as well as the collector current. Okay, collector current on y-axis, accelerating potential which is in x-axis. You know, so these are the points. This is about the first step. So what are the questions they have been asking? In briefly means what is spectra, spectral line spectra, what is the atomic spectra, discuss about the time. Okay. For an X-ray question, give an account of main characteristics of the light spectra and what are the empirical laws to be used there, and discuss about the Bohr's theory. After the expression, you need to write it down that what is the total kinetic energy or the potential energy to be calculated. Okay, for hydrogen atom, and also you have to draw the spectral lines of the hydrogen atom, and you have to give the importance of the course. Later, vector atomic model, how it could explain the fine structure of spectral lines. Whatever you spoke about that, what is L value, what is J value, what is S value. Later on, J equals to L plus S. Later on, Mj value, Ms value. Okay, all these two related to the vector atomic model. And you need to write it down the values, how these values are varying. You need to draw the figures also. That is very good. Finally, Frank circuits. Okay, this is about the first. Quantum numbers. You can see the contents. What are the contents? You can have quantum numbers on. So what is the correspondence principle? What are the quantum numbers? Pauli's exclusion principle. And the periodic table of an element, molecular spectra, which includes the electronic, rotational, and vibrational spectra. That's let me give you introduction about this here. So we shall study about the Bohr's correspondence principle as well as the Pauli's exclusion principle, which the spectra which can be how the spectra which can give means here emitted by an atoms due to energy change in their electronic system, which is known as atomic spectrum. When the element is in the molecular state, then the spectra emitted by the molecules which are known as band or molecular spectra. Okay, what do you say? Band. Band includes this spectral lines. If you are to be observe the band, uh, so that you can easily uh, find out the how the spectral lines which are to be closed here, each other. That is to be noted here. So when they spoke about the band here, definitely you have to say that the band includes the molecular spectrum. Okay. Next, here more spectra generally falls in three distinct regions. Wow, what are those regions? So you can easily observe that electromagnetic spectra. So that the electromagnetic spectra, which includes that here, what is that electromagnetic spectra? Radio waves, microwaves, infrared, visible, and here uh, visible region, infrared, and also here X-rays, gamma rays. Okay, so these are the different regions which can be observed. Okay, so in this spectra, there are three distinct regions to be observed here. What is that? First is the microwave or far infrared region here. Okay, so in infrared, IR is also you can easily near as well as the far IR regions you can easily observe. So one is that a microwave or far infrared region and near IR region, and the third one is that visible or near UV region. What is that UV? UV is the ultraviolet region. So that all these are to be observed in the case of electromagnetic spectra. Okay. So how the spinning of the electron in an atom, which was first proposed by the Goudsmit, okay, and Uhlenbeck. So these are the two scientists which was proposed by this in 1925. They have been explained the double line structure of the alkali metals. Okay. So here, according to that, each atom of an element of atomic number Z, you know pretty well, and which is built from the atom of the element of atomic number Z minus 1 by adding one more electron to the latter atom for keep the atom so formed neutral. It is too necessary to increase the nuclear change also corresponding. So what is the corresponding principle here? So Bohr proposed the theory of hydrogen atom. Here combining that here the both the classical as well as the quantum concepts. So when the quantum number, you know that small n is a quantum number here, which is very large. Successive values of the allowed energy values appears in the almost continuous, and similarly when the spectral what do you say here spectral lines approaches the series limit here, that is to be n equals to infinity, so that the spectrum appears almost continuous. So this behavior which led to the Bohr's postulate correspondence principle. So this principle states that the prediction of the quantum theory for the behavior of an atomic system must correspond to the prediction of the classical theory. When the quantum theory is taken to the classical limit for the quantum theory, which is the situation of transition between nearby the states having very large principal quantum. And also it can show that the quantum and classical theories which can give the identical prediction for the radiation energy. So Bohr used the corresponding principle to deduce the selection rules, which can apply to transition between the particular states in atoms. And regarding that classical electromagnetic theory, which can predict the frequency of the electromagnetic radiation, so nu equals to h by E, and which is equals to the frequency of revolution. or else under the limit of transition between the nearby states. Very large principal quantum number. The classical theory and Bohr's theory, the same results. So in this respect, the theories which have been satisfied the correspondence principle. What are the quantum numbers here? So here, according to that Bohr's as well as the here Sommerfeld theory, Bohr said that only in a circular orbit, hydrogen atom, regarding to the hydrogen atom, electron revolves, and which was corrected by the here Sommerfeld, which is an elliptical orbit. Because of these orbits, which played a very important role to develop the atomic structure here. So the Sommerfeld theory, which is showing that the electron in an only allowed energy levels of hydrogen atom may move in any one of the number of orbits. So that if n equals to 1, 2, 3, and so on, these are the possible orbits of the diagram of the allowed orbits for the first three energy levels. So you can see here, see here, see here. I'm zooming, see here. Okay. If you can see n equals to 1 means which is in circular. If you, n equals to 2 and L equals to 1, there also if n equals to 2, L equals to 0, L value. Okay. So there only you can observe that there is elliptical orbit as well as the circular orbit. So similarly for the top here, N1, L1, N3. 3 means 3P, 3S as well as the 3P, 3D. Okay. So these are the different orbits. Electron orbit for the hydrogen atom according to Bohr-Sommerfeld theory. GS means ground state level. So you have to explain with respect to an example here. You need to know that the total, the angular momentum, which is nothing but here mechanical momentum, PL equals to L into H by 2 pi or LH cross, like that. Okay. So you can easily observe that the spectral lines of hydrogen, lithium. Yeah, just now I already told you, sodium. You can see here, sodium. First 5890, 5896. What is the difference there? 6 angstroms. So combiningly, you have to say that 5890 plus 5896 divided by 2, 5893 angstroms for yellow color, sodium. So this is the spectral lines for Balmer series of hydrogen atom. H alpha, 1.59. In Balmer series only you can H. For spin and the orbital angular momentum, PS equals to SH by L 2 pi and PM equals to ML into H cross by 2 pi and MS PMS. That is a print mistake you can see here. 2.4 equation. Next, Pauli's exclusion principle. You need to know that here. What is principal quantum number N, orbital quantum number L, magnetic quantum number ML, as well as the spin projection quantum number, MS value. How these values are to be varying. Okay. So what is the Pauli's exclusion principle here? So here, according to that, no two electrons can exist in an atom in the same electron state. That means there is a difference between these spins here. That is to be noted here. The distribution of electron in different shell or subshells here. Shell means KLMN. Subshell means SPDF, like that. Okay. These are the N value, principal quantum number, azimuthal quantum number, orbital quantum numbers. Okay, ML and MS values. Yeah, already told you yesterday's class. Maximum number of electrons which can be here occupied by an orbit, that is nothing but 2n square. Okay. This is about the periodic table. This question is not asked at all, but how the electronic configuration and ionization energies which is to be varying here. So for hydrogen atom, ionization energy 13.6. Okay, very very important bit, objective bit. These are not famous, but let you have. Yeah, molecular spectra. When you spoke about the molecular spectra, which includes the electronic, rotational, as well as the vibrational, okay, spectra, so that how the transition between allowed energy states of these molecules is. So the energy in that of the atom here. So here you need to know that the electronic angular momentum, which is not conserved here, the molecules in the molecular energy state can be specified in terms of, for a diatomic molecule, diatomic means 2, N2, H2, okay, so that O2, so these are the diatomic molecules. What is the total energy distribution, which is symmetrical about the internuclear axis, but the component of the angular momentum about the axis is to be conserved, so which is to classify about the molecular energy states. Is that the nuclear motion molecules cannot be neglected. For a diatomic molecule, nuclear, why? So whenever such energy which is to be incidenting upon that, the atom which is to be absorbing such energy, so that due to that concept here, the electron which maybe vibrates, rotates, translate, which should be takes place here. But the entire system energy should be remains constant here, so that the energy of this vibrational rotational motion, which is to be quantized. So there are more energy levels in a molecular than in an atom. So that the analysis of the molecular spectra, which is difficult, but the proposed some models are there to explain about the molecular spectra. According to that, the excited energy levels of molecular fixed electronic configuration, which is due to ABC points, we have to write it down, and you have to give this. So this is about the molecular spectra. So what are the questions you may be expected in this Pauli's exclusion principle, and also write about the molecular and vibrational spectra. Elements of next one, elements of quantitative field. In this, we have to discuss about the photoelectric effect, Einstein's photoelectric equation, Compton effect. What is the dual nature of the light? What is the what are matter waves? And you have to know about the here experiment of Davison and Germer experiments, and also you need to know about the Thomson and Reid experiment, and the principle of complementary. Okay, and here what are the different concepts which are to be related to the matter waves, and also you need to know about the relation between the different velocities, and also
there may be a short question which is to be asking here. What is the relation between the group velocity as well as the particle velocity, and group velocity and the phase velocity? Okay, expected short questions, and also uncertainty principle. So that is to be noted here. These are the concepts. So let you know about that. What is the introduction of this? The development of the modern concept of the light quanta. Okay, so that the light which can travel in the form of radiation, that means which can be not in a near continuous manner, that is in a discrete manner. So that what is the discrete that is splitting here? You can easily find out that what is the energy of each quanta, that means which can travel by a wave packet. So the energy of the wave packet is equals to h nu. So which is related to quanta here? Who proposed this? Max Planck. Okay, please be noted here. So the photons, the energy of the photon equals to h nu. So that you can call it as a quanta name is a photon, which can begins with the Planck's idea, and also concerning a heat radiation. So that Newton, he have been proposed that the what is the hypothesis of light corpuscular theory, that light includes particles, so that which can travels not as a wave here, which can travel by a particles. That means the energy can be transferable through the particle only. Okay, that is related to the Newton corpuscular theory. But here some of the properties of the light which could not be explained successfully by the Newton corpuscular theory. Okay, later on Huygens, he have been proposed that not in a corpuscular theory, the light which can be passing with respect to the waves here. So wave includes the particle. Okay, so that is the concept which is to be enlightened by the here quantum mechanics, which is related to the which was proposed by the here Max Planck. So that's what here. If you are going to be observing the quanta energy of the quanta, the symbolic diagram which is to be representing here a wave. Okay, wave includes the particles. That is the concept. Whatever the failures which have been faced by the Newton corpuscular theory, the Huygens wave theory successfully explained. Okay, so the particle nature of the light got revived at the beginning of the century, and new experimental observations which is to be observed. So we have to study about the two phenomena, which is a photoelectric effect as well as the Compton effect. Okay, so which played a significant role in the development of the quantum theory here. And we have to study about the de Broglie wave, and which is associated with the moving particle here. Moving particle. Okay, so sometimes which behave like an electron, which behave like a particle, sometimes which behave like a wave here. Why? Because of a particle, electron is a particle, if you consider, which consists of a mass as well as the, it is to be having such a momentum, mass into velocity, mv, p equals to mv. So that which is a classical theory. Okay, but if it is behave like a wave, means E equals to h nu, like that, lambda equals to h by p, de Broglie wave theory. So lambda is the wavelength here. So h is the Planck's constant, p is the momentum. So lambda equals to h by mv or h by p here. So de Broglie wave, which is associated with the moving particle, the wave travels with the same velocity as that of the particle. So this wave velocity, which is also known as phase velocity. So that is to be noted here. W equals to V lambda, V and nu lambda. Nu and lambda is the frequency and wavelength of the wave. And you know pretty well, nu equals to E by h. E is the energy of the wave. H is the Planck's constant. And also, you know, the energy mass relation you proposed by this Einstein proposed, E equals to mc square, where m is the mass, c is the velocity of light. What is the value? 3 into 10 power 8 meter per second, or 3 into 10 power 10 centimeter per second. So here by combining these equations, nu equals to mc square by h, substituting w equals to mc square by lambda, lambda by h, using this de Broglie relation, lambda equals to h by mb, w equals to mc square by h into lambda by mb. There is a cancellation, m and get cancel, h and gets cancelled. Okay. So here this equation, two conclusions. One is that the wave velocity and the particle velocity are different, and some particle velocity is always less than that of the velocity of light, c value, and wave velocity w, which is always will be greater than that of the speed of the light. So that here there should be a contradiction between these two. What are those? Here the fundamentals of postulates of theory of relativity, who was proposed by the Einstein here. So to avoiding this difficulty concept of wave velocity or phase velocity and group velocity, which are made more clear. Okay. So by tomorrow's class, we will discuss about the photoelectric. Right. Thank you. Yeah. Any doubts regarding this, Geetika, Surya, baby Miriam? Any doubts? Hello. Yeah. Okay then. We'll meet on tomorrow's class.